Good afternoon, everyone. So I'm going to present my work on the electronic properties of two-dimensional transition metal Dichalcogenides from the iron, cobalt, nickel, and copper groups and their van der Waals heterostructures. So just a brief introduction. Transition metal Dichalcogenides are the materials with the chemical composition MQ2, combining a transition metal and a chalcogen, which is sulfur, selenium, or tellurium. These materials have been attracting a lot of attention in the context of two-dimensional materials, because when considering principally these materials, these transition metals that are highlighted in this table, they are obtaining layered crystal structures, which can be exfoliated to obtain monolayers or few layers nanosheets. And these layered crystal structures appear as polymorphs, which depend on the coordination environment of the transition metal. We have the trigonal prismatic coordination in the 2H phase. We have the octahedral coordination in the 1T phase, and the distorted octahedral coordination in the 1T prime phase. And this wide range of chemical compositions that can be obtained in these two-dimensional materials offers a lot of possibility to tune these properties by varying the chemical composition and also by alloying, and in the context of two-dimensional materials, by changing the number of layers in these materials. And this offers promising applications in several fields, going from nanoelectronics to thermoelectrics applications. One particular opportunity that these two-dimensional materials offer is the construction of van der Waals heterostructures, which is the combination of different monolayers by stacking, because you don't have the restrictions that in usual three-dimensional materials for the matching of these different materials in these junctions. And one of the potential applications of these van der Waals heterostructures is the solar cells. So, as I mentioned before, the transition metal Dichalcogenides from the early transition metals, principally the titanium, vanadium, and molybdenum groups, they have been widely explored in the past decade. And for example, we have in our group performed a comprehensive characterization of the structural parameters, the exfoliation energy, and also the electronic band gaps of the sulfides, selenides, and tellurides of these transition metals. But when considering the other transition metals, there's a diversity in the crystal structures that can be obtained. And this, including crystal structures that are not layered, they are not van der Waals layered structures. However, beyond the recent findings that theoretically indicate that also these compositions can be obtained as stable two-dimensional materials, we have some important recent results indicating the potential synthesis and stability of two-dimensional nanosheets and monolayers of materials that are not traditionally known as the van der Waals layered crystals. One important example is the exfoliation of hematite into the hematine monolayers. And also there is an interesting work on traditional 2,6 and 3,5 semiconductors. This is a theory that indicates the stability of double-layered honeycomb monolayers in these chemical compositions, more stable than the truncated bulk 3D phases. And because of that, there is an interest to explore the properties of two-dimensional materials, in our case specifically transition metal Dichalcogenides, in compositions that are not yet studied. So the goal of this work is to study the electronic band gaps of the bulk and monolayers transition metal Dichalcogenides from the iron, cobalt, nickel, and copper groups, principally to obtain the band offsets of the monolayers and characterize the band alignments of the van der Waals heterostructures that can be obtained with these monolayers in order to screen specifically these properties for the application of solar energy harvesting. We have done this by DFT calculations using the VASP software, where we employ the GGA-PBE functional, and also to obtain more realistic band gap values using the hybrid HSE06 functional. Also, because we are addressing the layered crystal structures, where London dispersion is an important energy thermal, we have included the D3 van der Waals corrections to describe the crystal structures of these materials. As I mentioned before, there's a lot of diversity in the crystal structures that can be obtained in this transition metal Dichalcogenides. And the transition metal and the crystal structures that we have selected in this study are the crystal structures that have been reported for transition metal Dichalcogenides in two crystal structures database. These are experimental results, the inorganic crystal structure database and the crystallographic open database. And these yielded 11 crystal structures, of which I highlight the 5 layered crystal structures, the 3 ones I have mentioned before, and also the palladium disulfide structure and the calaverite structure, which is a gold tellurite layered structure similar to the 1T structure. These structures I have called the 2D structures, but remember that they are also bulk structures, but layered structures. And we have 6 non-layered structures, which I have called 3D structures. For all these structures, for all these crystal structures, we have obtained the equilibrium geometries in all the compositions I have mentioned before. We have studied some properties such as the relative stability. We have addressed the structural properties and also the exfoliation energy of the layered bulk materials. But this is not the focus of the presentation today. I have discussed these properties in our previous workshop. Today I'm going to focus on the electronic properties. And to do this study of the electronic properties, we have employed the hybrid functional and selected the lowest energy 3D structure of each composition, the lowest energy 2D structure, and also the monolayer of these 2D structures. I show here the example of the nickel sulfide in the pyrite 1T and 1T monolayer phase, showing the electronic band structure and the local density of states, because the states here are important to discuss future property, and see that the primarily composition of the states comes from the D states of the transition metal and the P states of the chalcogen. Some general conclusions about this band structure results. We see that there's no occurrence of the direct to indirect band gap transition from monolayer to bulk. This type of transition is observed in the group 6 transition metal, the Dichalcogenides, the Dichalcogenides of molybdenum, tungsten, and so on. And so this absence of this occurrence of this band gap transition can be a problem for this class of materials. However, we see a similar feature, which is a decrease of the difference between the indirect band gap and direct band gap in our materials. We also see the expected increase in the band gap going to the monolayer limit due to the quantum confinement effects, and also that the strongest effect in the band gaps due to the layer stacking is observed in the group 10 materials, the materials of the nickel, palladium, and platinum. Here I show the band gaps of the semiconductors found among these materials, highlighting some band gaps in the region of the optimal band gaps for solar cells. And also, I emphasize that we have identified 17 semiconductor monolayers with band gaps going from 0.45 eV to 2.62 EV. These semiconductor monolayers are the 1T prime monolayers of the iron group, the palladium sulfide monolayer, and the 1T or calaverite monolayers, because they are very similar in these materials, for the remaining materials of the nickel group. This is a plot of the conduction band and valence band offsets of these semiconductor monolayers. And the trends that we can be observed here is that for common transition metal systems, the trends for substituting the chalcogen is that both the VBM and CBM energy levels increase with the atomic number of the chalcogen, because we are increasing the P energy levels, and also this leads to a stronger PD level repulsion that both increase the VBM and CBM energy levels. Because this effect is more direct and stronger in the VBM, the gap decreases when going from the sulfides to the tellurides. For the common chalcogen systems, we see that substitutions in the transition metal increase the CBM energy levels with the increase of the transition metal atomic number due to the more shallow D energy levels of the transition metals. As for the VBM, there's no clear trend found among all the materials, because here it's important interplay between the higher D energy levels of the transition metal, which would lead to a higher VBM, but also to this increase in the atomic number of the transition metal leads to a weaker level repulsion, because this orbital overlap becomes smaller. But in spite of that, the trend in the nickel group monolayers is clear, and it's dominated by the decrease of the PD level repulsion. And because of that, the VBM energy level decrease in this group when going from the nickel to the platinum sulfide. So as I mentioned before, one potential application of these two-dimensional materials is the construction of van der Waals heterostructures. And here I obtained the band alignments of van der Waals heterostructures, considering B layers, of all the pairs of semiconductors monolayers that I considered before. And this classification of semiconductor heterojunctions, the standard classification for semiconductor heterojunctions between type 1, type 2, and type 3, was done based on the Anderson rule, which is considering only the isolated band alignments, which I mentioned before. And this approach can be considered good for these monolayers because the coupling of these van der Waals layers is weak in the heterobi layer. The results in the classification that can be observed here could be expected based on the trends that I discussed before. For example, we see that most heterojunctions are type 2, the blue squares here, because we see that there was a clear trend of simultaneous increase of both the VBM and CBM energy levels in our band of sets and valence band of sets and conduction band of sets. But as in the nickel group monolayers, there's that trend of decreasing VBM while increasing the VBM. We see that type 1 heterojunctions are more common in the B layers that include the monolayers of the nickel group. So going to the potential application as solar energy harvesting for these heterobi layers, we have selected the type 2 heterojunctions and performed a simple estimate of the power conversion efficiency of these type 2 heterojunctions, which is based solely on the band gaps and the band offsets. The main goal of this simple estimate is just to compare these results for our class of materials with materials that have been more widely explored already for this application. For example, the molybdenum disulfide and tungsten disulfide junction with this model has an efficiency of 12%. So some details about this model. This model estimates the power conversion efficiency, employing a 0.65 efficiency solar cell fill factor, and a model for the open circuit voltage with an empirical factor of 0.30, and assuming 100% external quantum efficiency for the solar light absorption. Based on this model, we have obtained these values for power conversion efficiency, and these values are the 10 junctions with power conversion efficiency above 15%, and also above the one that is observed for the more traditional TMD 2D heterojunctions. And we see that only based on this criteria, this class of materials indicates a good potential for further investigations for application in solar cells. So this class of materials are good candidates for this application. Just a brief comment about this type of model. What property does it take to give a good efficiency in this model? And to illustrate that, I have selected the case with the highest efficiency, and this is the ruthenium telluride and osmium diselenide junction. And in this case, we have optimal donor band gap, 1.2 to 22 eV, which is an optimal band gap for the solar light absorption, also for the open circuit voltage. And we see also a small conduction band offset between the materials, which in this case is of only 0.02 eV. So to conclude, we have identified 17 semiconductor monolayers among the materials we have studied, from the 1T prime iron group, TMDs, and from the 1T calaverite nickel group and the palladium disulfide structure, with band gaps that go from 0.45 eV to 2.62 eV. The band offsets in these monolayers are determined primarily by the energies of the transition metal D energy levels and the P states of the chalcogen. There is an abundance of type 2 semiconductor heterojunctions in these van der Waals heterostructures, and based solely on the criteria of the band alignments and band gaps, this family of materials can be classified as good candidates for the application in photovoltaic devices. I'd like to thank the support for this work, and I thank the audience for the attention.